All right, hi everyone. In the last video, we looked at how to deal with related rates, and we walked through. I was going to say 7. It was really about 8 steps for how to deal with a related rates problem. In this video, we're going to look at 3 different examples. I've tried to pick different examples that use different geometric shapes, so it's not always the same formula or the same shape every time. So let's look at 3 different examples. The first one here says that air is being pumped into a spherical balloon, so think like a ball, so that its volume increases at a rate of 100 centimeters cubed per second. Now, I want to just stop and pause for a second. When it says centimeters cubed, that's only because it's talking about volume. So don't think you got to take the 100 and cube it or anything like that. The units are centimeters cubed per second. And when you hear a per second in there, you should hear a speed. There's a length divided by, or a distance divided by a time. And so that 100 centimeters cubed per second, it tells us a lot of information. We'll come back to that in a second. And the question says, how fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay, so if you remember our steps from the last video, the first step was to read carefully. So I even picked out a couple of things in there as we read through. First of all, kind of the second step there is that we had in the last video was to draw yourself a picture. So it's hard to draw a sphere. Here is my kind of a sphere. The dotted line is kind of on the back side of that. It's hard to draw a three-dimensional shape, but think about a balloon and this being filled up with air. Okay, so I know, there's my picture. It's amazing. And so if you think back to the other steps, we want to think about what information do we know and what do we not know, or better than saying what do we not know is what are we trying to find. Okay, so let's give labels to these. Right now we know something about 100 centimeters cubed per second, and so we got to think about what that is. It says, and then the question says, how fast is the radius of the ball increasing? Okay, I want to just focus on that part of the question for a second. How fast is the radius of the, I said ball, but balloon. How fast is the radius of the balloon increasing? What that is asking, anytime you hear something like how fast, you should interpret that as a speed. It wants to know about a rate. So how fast is the radius increasing? What we are asked, what we're trying to find is we are trying to find dr, which is r for radius, dt. Remember, all of our derivatives with related rates are going to have d something dt. This is what we're trying to find. Okay, so it's good to identify what the unknown is that we are looking for. But then there's another part of that last sentence. It says, how fast is the radius of the balloon increasing when the diameter is 50 centimeters? This is a little bit of a something to throw you off. Okay, something that you might say, well, wait a second, what about the diameter? Well, okay, but if the diameter is 50 centimeters, that just means that the radius is 25 centimeters. Remember, the radius is half of a circle, a diameter is all the way across the circle, and in this case we're just kind of talking about a three-dimensional circle, which is what a sphere or a balloon is. Okay, so question is, what is the 100 centimeters cubed per second? Again, that's a speed. That is actually how our volume is changing. When it says air is being pumped into the balloon so that the volume increases at a rate of 100 centimeters cubed per second, that is dV dt. So we don't necessarily know at the beginning, we don't need to know at the beginning how all these things relate to each other yet. We'll get there. We just want to be able to identify what information do we have in the problem. So when you see a value, you want to identify, is that value a fixed value or a changing value, and then what is that value representing? So the 100 centimeters cubed per second, that's talking about the volume. That's a dV dt. That volume is definitely changing. Okay, so volume is changing, and then the radius is also changing as you get more air in this balloon. As you put more air in, the balloon is getting bigger, the radius is expanding, the volume is increasing, and so you should expect that dr dt is not only changing, but since the other two values are both increasing, you should expect dr dt to be also, or you should expect the radius to be increasing. So you should actually expect dr dt to be a positive value since the radius is getting bigger and bigger. Now the question is, can we come up with a formula? If you remember from our steps in the last video, step number 5 was probably the most important step that says, can you come up with a formula for how to relate what you know to what you don't know? Okay, I don't know if you remember about the area for a volume of a sphere, maybe not, from a past class. Okay, you could look that one up. In this case, the volume of a sphere is 4/3 pi r cubed, and that's a constant formula. Like that's not like that's always the case. It's always the volume for a sphere. So then, could you take kind of go to step 6 in our last example of, could you take the derivative of both sides of this equation? This is the equation that relates v and r. And so could you take the derivative of both sides of this equation with respect to time t? Okay, take the derivative of the left side with respect to t, it would be dv dt. Take the derivative of the right side with respect to t, remember it's not with respect to r, so it's going to be 4/3 pi times, let's see, this is a power rule, so you get a 3r squared, but then don't forget that it's not just a 3r squared, you need a dr dt in there as well. So anytime you take a derivative, you need something with a something dt in it. Now go ahead and plug in what you know, and since we're trying to find dr dt, remember from the last page, that's kind of what we were looking for. We should know r and dv dt, we should know both of the other values that are there in that equation. So go ahead and plug in. dv dt was 100, so 100 equals 4/3 pi times 3. I know the 3's cancel out there, but just kind of writing it so that it shows up in the way that we would write it if we were taking a power rule. So r is 25, so 25 squared, and then times dr dt. Go ahead and solve for dr dt. Let's see, the 3's will cancel. 4 times, let's see, 25 squared in here, and then basically divide everything by the divide by everything that's not dr dt on the other side. So let's see, I haven't actually done this ahead of time, but 100 divided by 4 divided by another 25, I think you get something like 1/25 pi. Okay, because you're dividing by pi dividing by 25, and so that's what you should get for your dr dt. Now question, what are the units? Because we have units, this is a real world context problem. Okay, well, go back. Remember what dv dt looked like? It was centimeters cubed per second. This is not going to be centimeters cubed per second because we're talking about just the radius. This is going to be centimeters per second. Okay, so you could write this as a decimal, but here's what I got as a fraction. All right. So this is what we should get for this problem. Again, the hard part of this can be setting up the equation, and in this case it's really more about remembering this equation for the volume of a sphere, or at least looking that up or being able to find that. Okay, the equations for spheres we don't always, I think many of you might not always have those memorized, but when we get into two-dimensional shapes we should be able to recall those pretty quickly. Let's take a look at another example. This is a fun one. A ladder 10 foot long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Okay, so it feels like there's a lot of information in this problem. I would start, and let's go ahead and draw ourselves a picture and kind of see what this is going to look like, and we will kind of interpret the information that we have in the problem as we go. We have a vertical wall, which, despite my hand drawing picture, I think means we have a right angle there. And we have a 10-foot ladder. Now, again, question, one of the things we wanted to consider is what values are fixed and what values are changing. Okay, so one thing we should be able to identify is that this 10-foot ladder, this is actually a fixed value. The ladder's not getting shorter or longer as it falls. It's still 10 feet no matter where this is. Okay, so we want to think about kind of if you can kind of visualize this situation, the ladder is falling down this way, which means the bottom of the ladder is kind of kicking out away from the wall. All right, so it says if the bottom of the ladder slides away from the wall at a rate of 1 foot per second. I tell you what, let's give these some labels. 10 is going to be, if you think about this as a right triangle, 10 is going to be the hypotenuse of a right triangle. I'm going to call this x and this y. And so when it says that the bottom of the ladder slides away from the wall at a rate of 1 foot per second, what that's talking about is that dx dt, again, that's a speed in there, is 1 foot per second. Okay? And the question is, how fast is the top of the ladder sliding down the wall? So then hopefully from that, what we can pick out is that what we're trying to find, or what we don't know, is what is dy dt. That's what we're trying to find at the end. Okay? So we're also told to find dy dt when the bottom of the ladder is 6 feet from the wall. So when x equals 6. Now, again, we want to think about what's fixed and what's changing. And even though it says when x is 6, x is not always 6. X is changing. Remember, that value is getting bigger as the bottom of the ladder slides away from the wall. But at the instance that we're talking about, we care about when x is 6. So what we might want to find out, because it seems like we don't know this yet, is what is y at that point. Okay, we don't know y at that point. What we do know is that x is 6 and the ladder length is 10. Now, you may have this value memorized, or this Pythagorean triple memorized, but if you use a Pythagorean theorem, a common Pythagorean triple is a 6, 8, 10 triangle. So 6, 8, 10, which means that when x is 6 over here and your hypotenuse is 10, that means that y has to be 8 at that point. It's kind of like a 3, 4, 5 triangle, just double all the side lengths. So now we have 6, 8, 10, and so now we can look at setting up an equation for relating all the different sides. Hopefully the one that jumps to mind is the Pythagorean theorem that says that x squared plus y squared equals, call it z squared or c squared or whatever, but actually the ladder is a fixed length, so I'm going to call it 10 squared. Now this is an important feature. Notice in this equation where I used variables and where I used a constant. The x and the y are changing, so those get variables, but the 10 is fixed, so I'm just plugging in 10 into the equation. Okay. Now go ahead and take the derivative of both sides, remember, with respect to t. So this is 2x times dx dt plus 2y times dy dt equals, let's see, 10 squared is 100. That's still a constant. What's the derivative of a constant? Still 0, even when it's respect to t. Okay. Now we got to think about what information do we know and what are we trying to find. Let's go back to the last page. We know that x is 6. We know that y is 8. We know that dx dt is 1, and we are trying to find dy dt. So let's see. We know that x is 6. dx dt is 1. Y is 8. We're trying to find dy dt, so we don't have a value to plug in there, and this is all equal to 0. So once you plug in everything that you have, you should only have one unknown left, and so that unknown should be the thing that you're trying to solve for. If you have more than one unknown left, you might actually need to go and say, how could I find something else? For example, in this problem, if we didn't know that y was 8, because that wasn't given to us in the problem, we would have had this right here, and we would have had two things we don't know. But then we'd have to say, I know that I'm trying to find dy dt, could I go find y in the problem? Oh yeah, I could use the Pythagorean theorem, I know y has got to be 8. Okay, go ahead and simplify and solve for dy dt. This says that 12 plus 16 dy dt is equal to 0. That means that 16 dy dt equals negative 12, so dy dt equals negative 12 over 16. Okay, and you could reduce that, of course, divide by 4, that's negative 3 over 4, and the units on that are feet per second. Okay, so your units there need to be consistent, and so the last question I want to look at here in this problem is, why do we get a negative answer? Why does that make sense in the context of our problem to get a negative answer? Well, look at what y is. Okay, y is this length. That is a decreasing length as the ladder falls. So that's a negative value. Okay, we'll have to look at the next problem in the next video. Hope you enjoyed.